video we actually talk about as k varies across the root locus, how k varies. Okay, so let's take a look in terms of the so-called this graph over here. Okay, so the first thing first, when you typically are given any root locus, the first thing first, you actually have to plot the rows, the poles and zeros of the open loop transfer function. So take note that it must be open loop. Okay, open loop states that it is only k, and then you have a g of s, and then straightforward. So this is the in, this is the out. That's all. If it's closed loop, then you have a feedback loop. That's all. Okay. So with this concept, okay. So the first thing first, we define how many zeros are there, how many poles are there. So zeros equals to n, and then poles is equals to m. Okay. So this is just a notation everybody are using. Okay. And then next step is to actually to use rule tree. You have to visualize how your graph will move. Okay. So I don't know whether am I wrong or what. It says that the real axis which have an odd number of open loop singularities. These singularities means that either pole or zeros, okay, of the open loop. So what it means is any of these open loops, any of these open loop poles and zeros are called singularities. This is singularity, this is singularity, all of them are, okay. So as it says that any odd number of it to the right are on the locus. It should be not on the locus, right? As you can see, this is wait, hold on a while. Yeah. Okay, as you can see, this is singularity in odd number, right? This is 1. This is odd number. This is even number 2. This is 3. This is 4. Right? As you can see, as it is odd number, the this part over here, there is nothing. It is not part of the root locus, right? It is blank. And then in odd number 3, okay, this is the third one. There is also there is nothing in the root locus. Okay, this is empty. So as you can see, it says that the odd number of open loop singularities to the right are on the locus. So as you can see, to the right are not on the locus. Actually, it is to the left. Then is is on the locus. Okay, this is something I need to verify. Okay, but nonetheless, as you can see, you have that mindset. Okay, you can straight away draw to the even number will go to the left. Okay, and then if you have two poles, okay, side by side, if you doubt there are you can actually use double points calculation, and I'll show you. So with this rule tree, you can actually know that at this portion over here should be not on the locus. So this portion over here should not be in the locus, and this portion here should not be in the locus also, right? Because they are odd numbers to the right should not be in the locus. Okay, this is what it means. And then rule 4. The rule 4 start to talk about the asymptotes. Okay, when the asymptote is just simply saying that this is asymptote line. So any line, any curve that asymptotes to this line, asymptote line, is you never touch this line, but rather than you always follow this line. Let's say you have an asymptote over here. The curve itself will always go in this manner, but you will not touch the line. You will not touch the asymptote. You always stays there. Right. With this concept, what we need to do is actually to define where is this asymptote line lies at, right? So what we can do is actually to use this equation. Okay, don't ask me why, I also don't know, but it's a pretty much easy to use equation. Okay, so it's the summation of the poles value minus the summation of the zeros. Okay, so in this case, the values of the poles are -2, right? So you have -2 plus -3 plus -4, right? This is the amount of poles. So you summation the amount of poles. So 2, 3, 4. So it will be 9, minus 9, right? This is why we show over here is minus 9. And then the summation of the zeros is actually just only minus 1, right? Minus 1 plus 1, right? You may ask me why minus 1 or why this is minus 2, because whatever thing that makes this equation zeros, okay, whatever thing that makes the denominator 0 is poles, right? So these are all, this is your basic concept you need to know. So in order to make this equation 0, minus 3 has to be plus 3, minus 3 has to be s, so that minus 3 plus 3 equals to 0, the whole equation becomes to 0, and therefore this is the poles. I don't know why I'm repeating this, but yeah. So the summation of 0, there's only 1 zeros over here, so therefore it is minus. You can see it's minus, so minus 1, and divided by 2 is because it's n minus m. So this is why I say you need to remember this is the constant term that we're using to define poles and zeros. So m minus n, 3 minus 1 is equals to 2. So that's why we have 2. And then if you calculate, you have minus 4 over here. So this is why we have an asymptote lying on the minus 4 axis. Okay, as you can see, it's minus 4. So it's over here. And then, so the first thing first, typically you have to define all the poles and zeros. Second one is to define the asymptotes. I mean, at minus 4, right? Minus 4. And then the third one is actually to define the Q. Okay. Typically in the picture itself it says K, right? Because I don't want to confuse you the K with our K. Okay, then okay, where is it? Yeah. As you can see, this is the K, right? K360. This K is different from our controller K. Okay, it's different, totally different from this K. So don't be confused with that. This is why I actually use Q. So it's the same thing. Okay, but in this case, I'm trying to find the angles. Okay, whether is this asymptote, how many asymptotes are there? Okay, so from here you can actually see that this is an asymptote. This is the intersection point to the real axis only. I also need to know what are the angles of other asymptotes. Okay, in this case, we use this equation. Okay, this is the key equation, n minus m minus 1. Okay, so if you remember, this is the n is the number of poles. Okay, and then minus away the number of zeros, so you have 2. And then 2 minus 1 is equals to 1. So Q is equals to 0 and 1. This is why written over here. Later you understand why I put in why is 0 and 1. Okay, so as theta is equals to 180 divided by m minus n is actually 180 divided by m minus n is 2, right? And then plus k is actually 0 in this case for the first. From here you can actually know that there's two asymptotes. One asymptote is it's in this line, and another asymptote is this. Okay, so there are 90 degrees in this case. If it's 3 asymptotes, then you have like yeah, sorry. If it's 3 asymptotes, it should be in this manner. Okay, and then they have like this one over here, something like that. Okay, so I may not explain properly. Back to this case, we have only 2 asymptotes because we have 2 angles, 0. We have two constants, 0 and 1. So this equation will help us derive how many asymptotes do we have. So I repeat again, this equation helps us derive how many asymptotes do we have. Okay, or this one derive where is the center of asymptotes will be. Okay, so let's say if you're talking about 3 angles, right? I mean 3 asymptotes, right? If this is center of asymptotes, they will actually branch out from here. Okay, So if it's 3, let's say if it's like 0, 1, and 2, so if it's so you have certain angle, and you have 180. Okay, so in this case, if you were to, because our case is only 0 and 1, so in this case, if you were to plug in when it is 0, right, 180 divided by 2 is equal to 90 plus 0 divided by 2 is actually 0. So you have a asymptote in this direction, okay, 90 degrees, okay, because this is positive 90 degrees. And then when q is equals to 1, okay, you sub in back again, so it's multiplied by 1. So 180 divided by 2, this is n minus n, so we'll just rearrange. This is become 90 plus 180, you have 270. So at the center, 90, 180, 270. So this is why we have an angle over here also. So you have two asymptotes. So if these two asymptotes, the next thing you need to know is, okay, since we have two poles over here, and then this pole will not move towards this side, because whatever thing to the right of the odd number singularity, okay, this is odd number singularity, so whatever thing to the right should not be in the root locus. So we know that this will move in this manner, and then this one will move in this manner, because even number definitely, it should be within the root locus itself nonetheless. Okay, so definitely they will meet each other, and then they will cross path, and then they will move in this manner. So this is why it's actually shown over here, the same thing. So the next rule, so we talk about rule 4. Rule 4 consists of determining the asymptotes and the number of asymptotes. Okay, rule 4 is that. And then we talk about rule 3. Okay, is just to determine, the very first part is to determine whatever thing that is to the right of odd number singularity is not on the root locus. Okay, and then rule 7 is double point. Okay, in order to calculate the double points, okay, we can actually use rule 7, which is for, so far what I talk about the rule 4, rule 3 is actually 4.1.1, 4.1.3, sorry, 4.1.3, and then 4.1.4, and since we're talking about rule 7 is 4.1.7. Okay, so this double point is actually how does all this comes about. Okay, so I just show you. Remember, the characteristic equation is actually 1 plus kgs, right? I'm not going to repeat why. Okay, you should remember already. Okay, so in order to change, just rearrange only. So I divide the whole equation by k. Okay, so simply say I didn't change anything yet. I'm just trying to remove the k. Okay, I'm just trying to rearrange such that it becomes 1 over k plus gs. Okay, which is this one. You may doubt why. Okay, let's say this is 2. Let's say 1 plus 2 is equals to 5, right? If we introduce 1 over 2, okay, in this equation, so you cancel out the 2, and then you will have 1, 2. So half plus 2 is equals to 5. Okay, great. Okay, I may be wrong over here, but how we derive this is actually, I don't know what I write over here is wrong, so don't care about that. Okay, so if you remember, characteristic equation is 1 plus kgs is equals to 0, right? And then you just bring this forward, so you have kgs equals to minus 1, right? So the g of s is equals to minus 1 over k. And then for some reason they actually use a absolute value for 1 over k, so that's why you have 1 over k over here. Okay, nonetheless, if this is minus 1 over k, if you bring this back over here, you have 1 over k plus g of s equals to 0. This is how it's derived. So so it has to be equals to 0 in order to have a certain values. So in this case, what we can see is actually that 1 is equals to kgs. This is the meaning. Okay, so this kgs is equals to 1. This is always the case because they are equals to 0. This also explains why just now my examples go wrong. because my example said that it's 1, 2 equals to 5, right? It's not, it should be, they has to be the same, right? If this is 2, okay, this should be half, minus half, something like that. So it equals to 0, and then if you were to multiply with a 1 over 2, right? So this will be 1 over 2 plus it'll be, so you cancel away this, you have minus 1 over 2 equals to 0. So you end up, you still get equals to 0. So this is the portion you really need to understand. So I hope I didn't confuse you in this portion. And then with this said, the next thing we need to talk about is actually the how the next step. Okay, how we transition from this point to this point. We actually derived this already. So the next step is actually to rewrite this equation as this. Okay, how do we rewrite? So what it means over here is that for some values of k, okay, for some values of any values of k. So for some values of k, you maybe let's say k equals to 1, right? So this is 1 and this is 1. And then if you expand it, it will become x squared plus 3s plus 2 and then plus, so this one plus 3s plus 1s is equals to 4s and then plus 1 over here, so we have 3. And then if you were to rearrange back to a quadratic equation, is some values of s minus a squared. Okay, so with maybe some other you know, other s's remaining. If let's say you have three poles now, let's say you have s plus 3 in this case, then you may have extra s out over here. So this extra s out is actually the function to, okay, maybe some other functions. This is just how they rewrite it. But in this case, what you need to know truly is actually here. Okay, but I just derive, since there's only one step. So what is writing is actually to sum out, to do an equation. So he actually take f1. So you take this equation. So let's say 1 over k, g of s is equals to this portion over here, right? And then f to s, and then he differentiate with respect to s. So if you differentiate the whole equation with respect to s, okay, this equation becomes 0, or this equation becomes dgs over ds, right? So this, you differentiate this part, and it's equals to, you bring this 2 down, 2s minus a, and then since this is s1, you just multiply by 1, and then you keep the f2s because now this is the product rule, okay, and then plus, maybe I should expand this thing up, and then now we differentiate this part, so it should be pass f prime 2s, okay, this is a subscript, and then s minus a square, okay, it should be the case. Yeah, so this is how it derive. As you can see, it's exactly the same, okay, it's exactly the same over here, and s minus a square, I keep it, and then I differentiate the part over here, which is f prime lah, okay. In other words, it's df2 ds. It's the same portion. So as you can see that dgs divided ds is equals to this whole piece of information over here. Okay, but this still has a single root at s is equals to a. Okay, single root means that there will be, maybe I use different color. This two terms, okay, this term and this term share the same single root, which is this, right? So you sub in any values of s, okay, you have a, let's say your s is equals to a, you sub in a, this whole thing becomes 0, this whole thing becomes 0, right? Because they share the same roots, and therefore but this still has a single root and s equals to a. This is where when you sub s equals to a, the whole system becomes 0, and therefore it's equals to 0. So this is gs over ds is equals to 0. And therefore this is the how we derive for the double points, and how we're gonna use it for here. Okay. So I actually took the open loop transfer function without the k, okay, without the k. So let's take this open loop transfer function. I know I exceed 20 minutes already, but I just want to finish this part only. So this is the open loop transfer function. If we remove the k's, okay, what do we have? We only have this is the open loop transfer function. Hold on. What I paste is actually closed loop transfer function. What the hell? Okay. This is the open loop transfer function. Okay, damn it. When I remove the k, this is just without the k. So you differentiate this part. Okay, differentiate this part written in terms of s. Okay, so open loop transfer function normally you're given with k, right? So in this case, if you want to find double point, remove the k, and then you differentiate. Okay, so this portion here is this portion. So if you were to differentiate, okay, if you differentiate one time, it's just a quotient rule. So you differentiate, you keep s plus 1 over here is the same, and then you differentiate this portion over here, s plus 1 is equals to 1, and then you keep this portion over here, and then the whole thing square. It's equals to 0 as per we derive over here, and also shown over here. And then yeah, and then therefore when you expand it out, is I believe it's really tough. Okay, hold on. Okay, I only expand this portion over here. Okay, I only expand the numerator portion over here. I didn't expand this one because typically you want to find the roots only, the roots of the numerator. That's all. Typically you just want to find a double point. So as you can see, this thing is actually this portion over here, right? 3 dun dun. Okay, hold on. Yeah, definitely. So it's just 3s squared times s, and then 3s squared plus times 1, and then it's just multiplying 18s times s, 18s times 1, 26 times s, 26 times 1. So you have this portion over here. You may ask me why you differentiate, you only do this one, you don't want to do this one. Yeah, good question. Because if you remember, whatever thing that makes the equation 0 is actually the zeros, right? So who cares if this one goes to 0? I don't care, right? So if only this becomes 0, the whole equation becomes zeros. So this is why I take this portion over here. This is why I expand, and then I do a rearrangement. I have this equation, and then I go and find the roots. I have x1, x2, and x3. And you based on this values, let's paste, copy and paste, and okay, let's go over here. We have I expanded this portion. I expanded this graph into here. Okay, so let's compare with the root locus double point. Okay, as you can see, minus 0.1, it should be somewhere over here. It's not in the root locus, so it's cancelled. And then minus 3.5 is in the root locus, exactly the double point. So we have calculated the double point. And then what about minus 2.3473? Minus 2.34 is actually somewhere over here. It's also not in the root locus. So this also, so from here you can straight away see that the double point can be used to calculate, can be calculated through this method. Okay, so just to recap, I know it's very long-winded really. We talk about root 3. It's just whatever odd singularity. Okay, whatever odd singularity to the right is not in the root locus. Okay, so everything to the odd numbers of poles of zeros is always so-called it is always not in the root locus. That's all what I want to say. This is the rule 3. Then the rule 4 is just to simply find the asymptotes and the number of asymptotes and the angles of asymptotes. All about asymptotes. And then rule 7 is when you have double points. Okay, and then you can straight away use this one. You differentiate the open loop transfer function. You differentiate it, and then once you differentiate, you you only need to expand the numerator part, okay, and then you find the roots, and then you can straight away use the root because you already draw already ma. You just need to know whether which is the double point, what is the value. So this is why once you get the roots, you can actually know which is not in the root locus, which is in the root locus. So I hope I didn't confuse anything. I know it's very long. So I'll see you in the next video for the other rules. So this is only 3 rules. We have about 6 or 7 rules to go. So see you there.